Okay. I'm going to give you a kind of brief but whirlwind speed overview of the MEMS sensors on flexible substrates that we have developed towards the achievement of smart skin. What is smart skin? The way we define it is that it's an array of multifunctional sensors on a flexible substrate covered up with a flexible superstrate such that the sensors and the accompanying electronics, including power and readout circuitry, reside on the minimal strain plane. And these could be temperature, pressure, force, strain, acceleration, acoustic emission sensors. And now we're working on finding ways to power these using energy harvesting techniques. And the important thing about this is that we use our typical CMOS circuit, a CMOS fabrication equipment. That is just semiconductor fabrication equipment. And this allows us to use regular lithography, regular deposition techniques with limited temperature, and gives us a very small definition up to, down to a couple of hundred nanometers. That is in contrast to your typical inkjet printing, which you can probably get down to maybe a micron if you're lucky. So our immediate applications, and these applications are the applications we are working on. They're not all the applications, obviously. One of them is CPR sensors to provide feedback to the person who is administering the cardiopulmonary resuscitation such that the depth and the pressure is measured and a feedback is provided to the CPR administrator. The second thing is structural health monitoring. That is measuring the crack formation and the crack propagation and all related agents such as temperature, acceleration, etc. To monitor the structural health of, for example, airplanes and bridges, etc. Prosthetic skin. This is specifically important for upper body prostheses where the touch and feel is very, very important, where you would actually require submicron definition, spatial definition of the force. And we have been working on also these, both as a feedback, which is what we call tactile touch, also as a input, which is to be able to control the prosthesis through the motion of another body part. Other ones are intraocular pressure sensing. Again, very, very important. The nanometer scale of the sensor is very important in this case. Also, monitoring of cerebrospinal fluid shunts to relieve the fluid buildup in the brain, from the brain to the stomach. Predicted market growth for the flexible electronics, and this is the entire flexible electronics. As you can imagine, the majority is dominated by the display, the flexible displays as the source. So in 2012, if you look at this tiny little thing, it is still dominated by all of these displays. If you look at the sensors, and that percentage actually remains all throughout, all the way to 2018. So percentage-wise, sensors do not go up. However, the number goes up, which is important. So if I were to look at the amount of flexible sensors that's going to take place, predicted to be taking place in 2018, that amount is about equivalent to the entire amount of flexible electronics currently ongoing. So that gives us a lot of incentive, besides the fact that we would like to work on it, but that actually gives us a lot of applications. So the first thing I want to talk about is temperature sensors. And these are temperature sensors on, well, the temperature sensor is actually on one side of the flexible substrate, and the other side is the electrical connection side. Again, as I said, they are built using regular semiconductor processing equipment. So the bump bonds on the other side, we can define them down to 100 micron, a couple of 100 microns. And the temperature sensor, which is really a thermal sensor, is sitting right here in the middle. What you can see here when we build this, what you see here are the bump bonds on the other side, on one side, and the gold on the other side. It doesn't look, it's actually on the other side of the sheet, but because the sheet is transparent, you can see the gold. We use gold because of the good thermal conductivity. As I said, since we're using regular semiconductor processing technology, we can layer it as much as we want. We can define it down to nanometer scale. We can put them as close as possible. And we use a silicon carrier wafer, and at the end of the process, we actually peel it off. That's all we do. These are very fast, and they're linear response. And they show a very good resistance change with respect to temperature. Relative pressure sensors, they're actually what other people call force sensors, utilize a typical half Wheatstone bridge structure with two of the active sensors, piezoresistors, on the membrane, two outside the membrane. One of the things that we worry about is the inherent stress in these devices. Since the sensors sit on a membrane, a micromachine membrane, which is already a problem, causes a problem for stress in rigid substrates, it causes a little bit more problem on flexible substrates. But we were able to mitigate that issue and have minimal stress devices. Again, we are able to get fairly linear sensitivity. We can design these so that they are sensitive in a certain range and not sensitive above that, or not sensitive in a certain range and sensitivity increases. And that's just a design issue. And here is a plug of our University of Texas at Arlington, and you can see that the sensor is just wrapped around that. Absolute pressure sensors. In this case, what we do is, again, we have a Wheatstone bridge, but we put the sensors on top of a membrane which sits on top of a sealed cavity of known pressure. So that way we can measure the pressure in the environment with respect to that. Again, layers that we can define. This shows, the way we did this was the application defined the pitch of the sensors. We can actually put them a lot closer than that. It shows 75 pressure sensors in a 2 by 2 centimeters. Very linear output and excellent sensitivity. Accelerometers. These are your typical mass spring accelerometers, except they're on a flexible substrate. And again, we use the substrate-superstrate pair. The important thing here is that in packaging, we have to actually do a low-pressure packaging between the substrate and superstrate so that the damping is minimal. Excellent linearity. This shows capacitance change with respect to G, acceleration. And there is some hysteresis. The linearity is, this shows the second derivative of this line, so you want it to be 0, and that's exactly what it is. Sensitivity is 18 to 20 femtofarad per G. I'm not going to go too much into this. If there are questions, I can come back. Strain sensors on flexible substrates. As I mentioned before, we also do wafer level and device packaging. That's basically a substrate and superstrate with a device in the middle. Started doing this with microbolometers. And you can see, I don't know why it's doing that. Okay. You can see that very good isolation and very good encapsulation is possible. We've also done the same thing with accelerometers. This is actually looking at it through the superstrate, and you can see the proof mass and the spring of the accelerometer. We're right now working on acoustic emission sensors. The acoustic emission sensors are used for structural health monitoring. What happens is that when a crack forms in a structure, it actually emits an acoustic wave. It's a LAM wave that propagates along the material. If you can actually look at and understand the signature of this wave, you can build really skin-like sensors, flexible sensors that you can wrap around, for example, the airplane wing or a bridge structure or a bridge pillar, and you can detect it. This shows our membrane right here, and the entire thing, it doesn't show it here, but the entire thing is less than a millimeter here, and the z-axis is highly exaggerated. So this is again like a skin. We're also in the forum right now looking at using actually powering these sensors using the environmental vibration. This would take us, batteries are very important, of course, but we can use the vibrational energy of the environment to fill up the capacitors and fill up the power, and then that way recharge the batteries. Especially, I haven't talked about it here, but especially for biomedical applications, that's very, very important. For this purpose, we're looking at zinc oxide nanorods. These zinc oxide nanorods essentially grow perpendicular in z-axis. You really don't need to do too much. They want to grow. You have to actually try to have them grow horizontally. They're piezoelectric. So our aim is to be able to have these, control the growth of these, and then use it something like, think of it like a Band-Aid, where the sensors are in the middle of the Band-Aid, and think of it like a airy Band-Aid, where the zinc oxide nanorods are on it, and they can actually power the device. We have a poster upstairs on this, so you can actually get more information about it. So, I'm actually on time. As a conclusion, we have built flexible, self-packaged, self-powered sensors, which we call Smart Skin. We have demonstrated for different kinds of sensors figures of merit that are comparable or better to conventional sensors, meaning that they are actually for rigid sensors. We can integrate these, not right now, we haven't done it, but we would like to integrate these to polymer transistors and flexible displays and killer applications. I mean, we're just touching the tip of the iceberg right now for applications. Thank you.